Thank you, Anita. And it's good to see some faces from yesterday, and it's good to see some new faces. And today's topic is quite different from yesterday's topic. I'll be discussing dermal uptake directly from air of some common indoor pollutants. And the focus will be phthalates, but towards the end of the talk, I'll mention some experiments we've done on nicotine and hot off the press, BP3, benzophenone 3, a UV filter. Now, yesterday, I forgot to acknowledge my colleagues, and I realized last night that I had done that, and I felt very bad. So today I begin with acknowledgments. That way I won't forget. So the work I'm about to describe is the result of quite a team. We've got individuals from the Technical University of Denmark. Some of you know these individuals: Gabriel Biko, Jorn Tuftum, Geo Clausen. The urine analyses have been done by Holger Koch at the Institute of Ruhr University Bochum, and Holger is world famous for the techniques he's developed to identify different metabolites of compounds in urine and in blood. The air analyses were done by Tunga Salthammer and Tobias Schripp. Glenn Morrison conceived of and executed the clothing experiments I'll describe. He was at Missouri University of Science and Technology. He's now at University of North Carolina. He just started there a month ago. And Lulu, my wife, assisted in some of these experiments, and I thank her for that. She's also a chemist. And here's the pictures of some of the people I mentioned: Holger Koch, Glenn Morrison, Tunga, Gabriel, Gil Clausen, Jorn Tuften, my wife, Lulu, Glenn Morrison, and Tobias. Lulu is not short. Glenn and Tobias are tall. Okay, so uptake of small organic molecules directly from air through our skin. This has been known for some time, and the pioneering work was done by a Polish scientist, Piotrowski, and Piotrowski did experiments published in 1967 and 1971. He had his subjects breathe clean air in a room while he exposed them first to nitrophenol I said nitrophenol, nitrobenzene, yes, first nitrobenzene and then phenol. And he collected their urine for several days. He knew that the only way these compounds could have gotten into them, since they were breathing clean air, was through the skin. And he showed that for these two small organic molecules, uptake through the skin was quite large. Altogether, there have been about 20 such studies of small organic molecules demonstrating significant uptake from the air. This particular picture comes from a study by Bader et al. In 2008. I showed it because it gives you a sense of how the clean air is delivered. There's different ways that people deliver clean air. In a moment, you'll see how we've done it in our own experiments. In the Bader experiments, they were looking at N-methyl-2 pyrrolidone, NMP, and again, they saw significant dermal uptake. In the case of higher molecular weight organic compounds, semi-volatile organic compounds, prior to the work I'm going to describe, there were no comparable experiments to those I've just described by Piotrowski and Bader and others. Although there was plenty of evidence that SVOCs, once they get on the skin, can pass through the skin. You're all familiar with dermal patches to help people quit smoking, dermal patches that contain nicotine. Well, obviously, there's a situation where you're putting the nicotine on the skin and it's finding its way to the blood. Otherwise, the patch wouldn't be effective. The Israeli army treats their military uniforms with permethrin, an insecticide, and studies have been done showing that when the soldiers wear the permethrin-treated uniforms, you can find the permethrin in the urine. So again, evidence for uptake through the skin of a relatively large molecular weight molecule. A group in Denmark, in Copenhagen, looked at creams that were deliberately formulated to contain phthalate esters and parabens, and they saw that when those creams were applied to the skin, there was significant uptake of the two phthalates they looked at in the paraben. So there were these kind of studies, but nothing looking at direct uptake from air. So what has to happen for a chemical to get from the air into our blood? It first has to pass through a boundary layer of air adjacent to our skin. It then goes through this very thin layer of skin oil and encounters the stratum corneum. And if the molecule is lipophilic, and those are the kind of compounds we're talking about, a molecule that likes fat, if it's lipophilic, it will go through this lipid bilayer, a relatively tortuous path, to get through the stratum corneum and to the viable epidermis. Now, the viable epidermis is primarily water. It's an aqueous layer. So then the molecule has to make it across this aqueous layer to reach the dermal capillaries. That's what's involved in getting from air in the core of a room to blood. Now, we developed a very simple model to describe this process. It's a mass transport model. We're treating each of these steps I mentioned as a resistor, and we just treat it as resistors in series. So to calculate an overall permeability coefficient for a compound from room air to blood, we, as I said, treat it as resistors in series. So the reciprocal of this overall permeability coefficient is the sum of these two, the reciprocal of these two resistances. Transport from air to air at the surface of skin, and transport from air at the surface of skin to blood. And this particular process can be broken down, if you want to, into two processes: transport across the stratum corneum and transport across the viable epidermis. So that's the model. And Bill Nazaroff and I applied that model to a large number of different compounds. We looked at common indoor pollutants, and what this figure attempts to summarize is for a large number of common indoor pollutants, it gives you a sense of those indoor pollutants that go through the skin from air fairly readily, and those that do almost nothing. So the compounds over here on the left of the figure, these are compounds that have small values for the permeability coefficient. So these compounds, the skin is a terrific barrier. These compounds don't get through the skin. The compounds that I've circled in red, the compounds on the right, these are compounds with higher values for the permeability coefficients. These are compounds that we feel you have to consider dermal uptake as one potential pathway when you evaluate exposure. A lot of these compounds are well known. If you work in the indoor environment, you know the phthalate esters. You see synthetic musts here: galaxide, tonalide, phthalate, parabens, ethylparaben, propylparaben, butylparaben, some terpene alcohols. So a large number of compounds that we think warrant attention when you're evaluating overall exposure, that you really should think about the dermal pathway. Well, talking to my friends at DTU and elsewhere, we thought it was time to do some experiments. And we decided to begin with diethyl phthalate and diambutyl phthalate, and to take advantage of the chambers at the Technical University of Denmark. Why DEP and DNBP? Well, in urine samples in the developed world, these two phthalates, actually their metabolites, are often the most abundant man-made compounds in the urine. Our exposure is quite large. We're exposed from so many different materials. So they're common in the urine. Diethyl phthalate is used in a lot of personal care products. It's a carrier for scents. It's a solvent. Diambutyl phthalate is used as a plasticizer, not just in polymers, but it's also not just in PVC. It's also used in nail polish, for example. So many uses for these two compounds. And our modeling studies indicated that both of these compounds are taken up directly from air at significant rates. And importantly, although both of these compounds are present in our diet is not the major pathway for these two compounds. So Holger Koch had done fasting studies of individuals, and when he puts individuals on a 48-hour fast, the concentration of something like di-2-ethylhexyl phthalate and even larger molecular weight phthalate, that goes down almost to zero. But the concentration of these two phthalates, although they decrease, it's apparent that other pathways are important besides the diet for these two phthalates. So how were the experiments designed? we had 6 volunteers. Actually, we were our own subjects in these experiments. When I say we, I mean the investigators. In the first week, on Tuesday, we had group 1. We had 3 people in the chamber at a time. So 6 people, 2 groups, group 1 and group 2. Group 1 was exposed in the chamber for 6 hours while they were wearing these breathing hoods. On Wednesday, group 2 was exposed in the chamber for 6 hours, but they didn't wear the hoods. So they were both breathing and bringing in the phthalates through their skin. And on the second week, things were simply flipped. Group 1 was exposed without hoods on Tuesday. Group 2 was exposed wearing hoods. Now, we did go on a restricted diet before we began these exposures to limit the background concentrations of phthalates in our urine, or the metabolites in our urine. So our restricted diet was Vasa Sport, for those of you who know Vasa Sport, and tap water, only tap water, no bottled water, and fruits with thick skin. That was it. And it was a diet that you got tired of very quickly. And it made you appreciate real food when the experiment was over. But it also worked. It also really brought down our background levels for these 2 phthalates. So here is a picture of us in the chamber, and you see how we delivered the clean air. It's a breathing hood. We actually got the idea from Riggs Hospitalet. They have a hyperbaric chamber, and this is the type of hood that the subjects wear at the hospital when they're in the hyperbaric chamber. But these hoods worked quite well. So that's delivering clean air, and the exposure is only through the skin. And here is the timeline. So the restricted diet began 12 hours before the exposure. The exposure itself was 6 hours. The urine collection began, we took 2 samples before the exposure itself, and then we collected urine until 54 hours after we began the exposure. And we began air sampling before the volunteers went into the chamber and continued sampling the air every hour while the volunteers were in the chamber. So we know well what the air concentrations were. So here are the results. And I'm going to try and talk through this slowly. There's a lot of information on it. The y-axis is the concentration in the urine of the 3 metabolites that we were following. MEP is a metabolite of diethyl phthalate. MNBP is a metabolite of diambutyl phthalate. And 3-hydroxy-MNBP is also a metabolite of diambutyl phthalate. So let's begin with this red curve with the open triangles. This is showing the concentration of MEP in the urine when a subject is not wearing a hood. So this is a combination of dermal uptake and inhalation together. This, by the way, is for just one subject. This is subject number 3. Now, if we look at the next trace down, the solid red triangles, that's the same subject, but wearing the hood. Okay, so breathing clean air. The only pathway for the solid red triangles is dermal uptake. And you see that it's not as high as when the individual is exposed without the hood, but it's still a significant uptake of DEP. And if we look at the next traces, the green open circles and the green solid circles, that's MNBP, we see something similar. Without the hood and with the hood. So less when wearing the hood, but it's not down here. It's a significant uptake through the skin. And for the final metabolite, again, the same behavior. This is without the hood, both breathing and skin. This is with the hood, only dermal uptake. Significant. Here are the results for all 6 subjects, and you see some variation there from subject to subject. But what you see for all 6 subjects is significant dermal uptake as evidenced by these three metabolites. Significant dermal uptake of both diethyl phthalate and di-N-butyl phthalate. Here's another way to view the same data. On these plots, the y-axis is now linear, and we're looking at the net amount of either MEP, that's this figure, or MNBP, that's this figure, that has been excreted in urine at a particular point in time. So the x-axis is the time axis. So exposure begins there. Remember, I told you that the exposure is 6 hours. And you can see how the amount, this is the amount excreted when not wearing a hood. This is the amount excreted when wearing a hood. And it's about half, when wearing a hood, the dermal uptake is about half of what the uptake is when it's inhalation and dermal together. When wearing a hood, it's not down here, it's a significant uptake. And we see something similar in the case of the metabolite of di-N-butyl phthalate, MNBP. And once again, I showed these plots for all 6 of the subjects. And you see that for some subjects, the dermal uptake is closer to the combination of dermal and inhalation. And for some subjects, the difference is greater. And just reflecting individual differences in terms of the permeability of their skin. So from the concentrations of the metabolites in the urine, we can back calculate the uptake from the air. And this slide shows the micrograms of phthalate absorbed divided by the concentration of the phthalate in the air. And these are box whisker plots for all 6 subjects. And I grant you that a box whisker plot for N of 6 is a little bit weird, but it's a convenient way to show the results. So without the hood, the median value for diethyl phthalate is about 8 micrograms of phthalate absorbed per microgram per cubic meter of phthalate in the air. With the hood, the median value is about 4. And by subtracting the hood value from the no hood value, we get what was taken up simply by inhalation, by breathing. Now, there's something very pleasing about the fact that the breathing value here is close to 4, and the breathing value for di-N-butyl phthalate is close to 4. Think about it. Think about what this y-axis is showing us. Micrograms of phthalate absorbed per air concentration. Well, in effect, for inhalation, this is going to be the volume of air that was breathed during the exposure period. The exposure period was 6 hours. These are males at rest, adult males at rest. And an adult male at rest breathes about 7/10 of a cubic meter an hour. So 6 hours times 7/10 of a cubic meter an hour, 4.2 cubic meters. So the fact that this turns out to be close to 4 for both of the phthalates, that's reassuring. It indicates that we're doing something right. The skin is a reservoir for these phthalates. The exposure is 6 hours, but we continue to have the metabolites in our urine for an extended period of time. And that's what I'm trying to emphasize on this slide. So for each of the 6 subjects, I'm showing the amount of MNBP, that's the metabolite of di-N-butyl phthalate, the amount excreted in the first 2 urinations after exposure began, and in all the subsequent urinations. So the first 2 urinations after exposure begins, it's only a fraction of what ultimately winds up coming out. Well, that's uptake from air through bare skin. What about clothing? What's the role of clothing in this process? And as I mentioned, it's Glenn Morrison who conceived of these experiments and made them happen. So we're focusing on this pathway where a chemical sorbs to clothing we wear that clothing, and it goes from the clothing through our skin, and we metabolize it. Now, in these experiments that Glenn designed, he felt it made sense to look at two scenarios. One, where you're in the chamber with freshly washed clothing, freshly laundered clothing. That's the first exposure. And then the second exposure he did the following week. He had the clothes in the chamber exposed to the phthalates for 9 days. And he wore those clothes that had been exposed to the phthalates in the chamber in the second set of experiments. Once again, restricted diet, no use of personal care products, and urine samples collected for 54 hours after entering the chamber. Here you see the clothes being exposed in the chamber. And as I said, it was for 9 days that they were exposed before being worn in the second week. And there Glenn is wearing, I think, fresh clothes in that case. I don't know. So, results. We're looking at MEP on this slide and NBP on this slide. And we're looking at net amount excreted over time. Again, the y-axis is linear. This line in the middle, that's for a bare-skinned subject who's comparable to the volunteer wearing clothing in terms of age and size. This is when fresh clothes are worn. So compared to bare skin, the fresh clothes really retard uptake. The fresh clothes are serving as a barrier, if you will. This is the exposed clothes. And you see that the uptake is amplified when you wear the clothes that have been exposed to the diethyl phthalate and di-N-butyl phthalate. And if you look closely, there's another difference here. The clothing is more protective in the case of di-N-butyl phthalate than it is diethyl phthalate. And it doesn't show as strongly here as it will in the next slide, but the clothing amplifies the exposure more in the case of di-N-butyl phthalate than diethyl phthalate. That's more apparent on this slide. So here, the open square for this DEP figure is the normalized uptake of diethyl phthalate when fresh clothes are worn. This is the box whisker plot for the 6 bare-skinned subject. And the black square, that's the normalized uptake when exposed clothes are worn for diethyl phthalate. And analogous results for di-N-butyl phthalate. And as it states here, all results are for exposures that occurred while wearing the hood. So this is only the dermal pathway. And you see that this open square is higher than this open square. The clothing is more protective for di-N-butyl phthalate. And this solid black square is higher than this solid black square. The clothing amplifies uptake for DNBP more than DEP. Why is this? Well, cotton likes phthalate esters. If you try to measure the partition coefficient for a phthalate ester between air and clothing, you get very large numbers. This particular plot shows attempts to do just that. This particular line is for di-N-butyl phthalate. This line is for diethyl phthalate. What's being measured is the uptake of these compounds by what was, to begin with, a clean t-shirt. And you see how that changes with the air concentration. But the partition coefficient for di-N-butyl phthalate is significantly larger than the partition coefficient for diethyl phthalate. So, a clean shirt has a much larger capacity for di-N-butyl phthalate than for diethyl phthalate. A clean shirt will serve as a barrier for uptake until that capacity is overwhelmed. So, this is why the clean shirts offer more protection in the case of di-N-butyl phthalate, more capacity for di-N-butyl phthalate. When the shirt's been exposed in the chamber for 9 days, the shirt has a higher concentration of di-N-butyl phthalate than it does diethyl phthalate. And that's why the shirt delivers more dian-butyl phthalate to the volunteer after it's been exposed for 9 days than it does diethyl phthalate. Okay, that's what I wanted to say about phthalate. Now let's move on to nicotine. We chose nicotine as our next compound because although we know nicotine gets through the skin because patches work, we weren't sure if nicotine would pass from the air through the skin to blood. Our skin, its pH is somewhere between 5 and 6. And nicotine is a base. And the pKa of monoprotonated nicotine is around 8. So that means if nicotine is present in an aqueous film on our skin, it's primarily protonated. And protonated nicotine does not go through the skin very well. Protonated nicotine goes through the skin about 50 times slower than base neutral nicotine. So we were wondering, is the protonation of nicotine at the surface of our skin going to basically mean this doesn't happen? And the experiments show that it does happen. But before I show you that, a little background. The uptake of nicotine through the skin is known in extreme examples, has been known for some time. This is a paper that appeared in Journal of American Medical Association in 1933. And it talks about the death of a pharmacist who had a small vial of nicotine in his hip pocket and sat on it, and it broke, and he didn't attend to it immediately, and he wound up about 24 hours later dead. It's a sobering paper to read. And the individuals who harvest tobacco leaves, they're encouraged to use impermeable gloves, and poisoning of people who harvest green tobacco, that's been known for some time. Our initial experiments at DTU, we wanted to do some relatively quick and dirty experiments just to answer this question of nicotine being protonated and the extent to which that occurs. So Nico, who handles our shop, he built this smoking machine. And I think it's very clever. It's just a tube with a muffin fan on one end, and it can smoke up to 10 cigarettes at a time. In our experiments, we had the machine only smoking 3 cigarettes. This is our exposure chamber, and you notice that for these nicotine experiments, we've covered the wall of the chamber with polyethylene, the kind you'd use if you were painting. You all know the way cigarette smoke hangs around, and we did not want to contaminate the chamber with the cigarette smoke. And this worked very well. When we got rid of the polyethylene, the chamber was fresh. I mean, you could walk in and there was no smell of the fact that the smoking had occurred there. But when the smoking was going on, this chamber reeked. I found it really offensive. We had 3-hour exposures, wearing the hood, breathing clean air, and as I said, 3 cigarettes continuously being smoked during the period. The average nicotine concentration in the air was 475 micrograms per cubic meter. That seems awfully high, right? But those are the kind of levels that were measured in British pubs, back when smoking was common in pubs. And those of you who are older, you've probably all been in a pub or a tavern or a situation where you've experienced those kind of levels. Okay. We collected baseline samples of urine. We did not have to go on a special diet for nicotine. This is good. There are foods that contain nicotine. Tomatoes, for example, contain small amounts of nicotine, but not enough to worry about. Our baseline levels were all good, and we just had to avoid tobacco smoke, avoid people who were smoking prior to and during these experiments. Because these were pilot experiments, we pooled the samples. So our first pool was all the urine between 0 and 12 hours, the next all the urine between 12 and 36, and the final all the urine between 36 and 30. And we monitored in the urine nicotine and 2 metabolites, cotinine and hydroxycotinine. This is subject number 1, the net amount excreted of nicotine, the blue line, of cotinine, the red line, and of 3-hydroxycotinine, the green line. And this is indicative of significant dermal uptake. So right away, you see this plot and you know that the protonation of nicotine on the skin was not significantly impacting the uptake of nicotine. So we still don't know why that is. We can speculate that maybe our skin has islands of moisture and islands of skin oil, and maybe the nicotine is going through the islands of skin oil. But the fact is, the nicotine is getting in directly from air. Here are the results for subject 2. You see that the metabolism is slightly different between these two subjects. I'll just go back and forth. But again, the excretion of the metabolites and nicotine itself is indicating significant dermal uptake. And then our volunteer wearing fresh clothes, and the y-axis has been changed now. This is a smaller y-axis. The fresh clothes were very protective in terms of the nicotine. And here we are with a shirt, just a shirt that had been exposed to nicotine. We didn't do all the clothing. We were afraid it might be too high. As it turns out, the uptake is not as high from the clothing as it is for something like diane-butyl phthalate, because the capacity of the clothing for nicotine is less than the capacity of the clothing for the phthalates. But you still have significant uptake from the clothing that's been exposed to the nicotine. And on this slide, we compare a calculated inhalation intake to measured dermal uptake. And we did no experiments here where we were in the chamber without the hood. We only wanted to be in that chamber with the hood. As I said, it was foul in there. Here, the inhalation intake is simply the known concentration of nicotine times our estimated breathing rate. That's how we get inhalation in this case. So you see, dermal uptake from air is only a little bit smaller than what inhalation would have been under those same conditions. This is a pathway that's been neglected when people do analyses of exposures to nicotine in homes where individuals smoke. You see these kind of exposure assessments when people think about the impact of parents smoking on infants. And they calculate how much the infants are taking up by breathing, but they're ignoring this pathway, which is almost as important as breathing. Okay, let's put these levels in context that we measured. What we measured in our urine was an order of magnitude, 10 times higher than our baseline values, or what you would see for non-smokers who avoided ETS. It was comparable to what you would see for non-smokers at something like a bingo game when smoking was occurring before the smoking ban. It was about half that you would measure in someone who was a light smoker, who was smoking maybe 4 to 6 cigarettes a day. Okay, given that pilot experiment, it was time to move on to a full-scale experiment. So more subjects, and we were criticized in terms of that pilot experiment. There were individuals who said, how do you know that the particles weren't playing a role in the delivery of nicotine to the skin? Well, we did calculations to try and convince them that the particles could only make a small contribution. But just to avoid that issue completely, in this next set of experiments, rather than use cigarettes, where you have lots of smoke in the air, we had only pure nicotine. So we delivered nicotine to the chamber using this syringe pump. And the syringe pump allowed us to deliver the nicotine. Actually, it's a solution of nicotine and water. Allowed us to deliver it very accurately. And the chambers at DTU are controlled very well. The air exchange rate is very carefully controlled. So we had rock steady levels of nicotine in the chamber. This is the design for the more detailed experiments. By the way, the paper describing this has just been submitted, so you're hearing information that you're among the first people to hear these results. In these experiments, the exposure lasted 5 hours, and all of the subjects wore hoods and breathed clean air. We had no experiments where the subjects did not wear hood. In week 1, we had 4 subjects who were bare-skinned, 1, 3, 2, and 4. And we had 2 subjects who wore fresh clothes, subject 5 and subject 6. And then in week 2, we had 2 bare-skinned subjects. P3 came back, and P4 came back from week 1. And we had subject 5 now wearing a shirt and gloves and socks that had been exposed to nicotine, and subject 6 also wearing the clothes that had been exposed to nicotine. So that's the experimental design. And you see subject P3 with a shower here and subject P4 with a shower. So the difference between the exposure for these subjects in week 1 and week 2 was that immediately after they left the chamber in week 2, they took a shower. How much does it help to shower immediately after you've been exposed to nicotine? Does it help? That's the question we were trying to address there. Here you see the clothes exposed in the chamber to nicotine. And here are the nicotine concentrations. And this is showing something different that I think is fun. When there are no occupants in the chamber, the nicotine level around 320 micrograms per cubic meter. And this is, as I said earlier, it's rock steady. It's because we've got the syringe pump, the temperature is controlled, the air exchange rate is controlled. 3 people go into the chamber, 2 bare-skinned, 1 with fresh clothes, and that level goes from 324 to 236. The people are async. You see it going down. And you see that it's relatively reproducible, even though the net surface area is different for the 3 people. But, from 324 to 236 or 240, because you've introduced 3 bodies. In the second week, we only had 2 bodies in there. So we don't go down as much, 304 and 281. I think that's just a nice demonstration of the fact that human occupants can be sinks for certain semi-volatile organic compounds that sorb to the clothing and sorb to the skin and hair. Here are all of the results summarized in one slide for this study. The blue bars, these blue bars are for the bare-skinned subjects. And over here, we have the clothing experiments. And what we're looking at is the nicotine uptake, back calculated from the metabolites, normalized by the air concentration and also the body surface area. And we had to normalize by the air concentration because it's different in week 1 with 3 subjects and week 2 with 2 subjects. And you see the total uptake of nicotine varies among the 4 subjects. In the case of subject P3, this is the first week where the subject did not shower. This is the second week where the subject showered immediately after. For subject 3, the showering had a large effect. The uptake was reduced by a factor of 2 because of that shower. For subject 4, very different story. For subject 4, there was only a slight effect of showering. We don't know what's going on. We realized afterwards that we should have been more careful in terms of telling people how to shower. We allowed individuals to use whatever soap, whatever products they wanted in the shower. We didn't say anything about how hot the water should be or how long the shower should be. Is part of this difference between subject 3 and subject 4 simply the fact that they showered differently? Or does it reflect the fact that subject 4 is older than subject 3? And does it say something about the amount of skin surface lipids and the residue of nicotine that could readily be washed off? Was that greater for subject 3 than subject 4? We've done lots of speculation. What we have to do is more experiments, and we are planning on looking at this particular aspect more carefully. this gray shaded area, that's what you would anticipate from inhalation. So this is what if it was inhalation alone, this is the kind of uptake you would expect, normalized by body surface area and air concentration. So you see that for 2 of the subjects, their uptake was actually slightly larger than you'd expect from inhalation. This is pure nicotine, no smoke or other compounds to confuse the situation. Oh, and clothing? The fresh clothes, again, provided nice protection from the nicotine. And with the exposed clothes, it's interesting that subject 6 had a larger uptake, almost twice as large, as subject 5, wearing the same exposed clothes. And part of that we think might be age difference, and other factors we're not sure. But there are these subject-to-subject differences in terms of our permeability to different chemicals. Well, I'll finish up by saying a little bit about our work with benzophenone 3, BP3. BP3 is present in a lot of sunscreens. So if you lather up with sunscreen in the summer, if you spray yourself with something in the summer to prevent sunburn, odds are at some point you've been exposed to BP3. But that's not the only source of exposure to BP3. Many different materials contain UV blockers to slow down the rate at which the materials degrade. So, I don't know about the lacquer on this table, but some lacquers contain UV blockers. And certain fabrics where you don't want the color to fade quickly, they'll have UV blockers in them. UV blockers are so common that if you sample dust or air, this is a compound you find in indoor dust and indoor air, simply because of the common use of these UV blockers in materials. So yes, we're exposed to BP3 when we use a sunscreen, but we're also exposed in the middle of winter because it's part of our indoor environment. And here it looked from those calculations that Bill Nazaroff and I had done that this was another compound that would have a high permeability coefficient. In these experiments, the BP3, I'll go back to this. In these experiments, clothing was exposed to BP3, and then 3 subjects wore the clothing that had been exposed to BP3. And in these experiments, both blood samples and urine samples were collected. The blood samples were collected over the initial 6-hour period after the t-shirts had been worn. The t-shirts were worn for 3 hours. I'm just showing the results for BP3 in urine and its metabolite BP1. And here you see the results for BP1, the metabolite, for the 3 different volunteers. And you see the cumulative amount excreted in urine. Participant 3 had much more uptake than participant 2, who had more uptake than participant 1. And here are the results for BP3, the parent, and again, participant 3, more uptake than participant 2 than participant 1. But they all had significant uptake simply by wearing this shirt that had been exposed to BP3. Here's another way to look at the data. We're looking here at the excretion rate, micrograms per hour, of BP1 and BP3 summed together. And the exposure, 3 hours, this is the exposure itself, and the excretion rate peaks right around the end of the exposure, that urination. But it continues for some time at an elevated level. Well, that covers what I wanted to say this morning. Dermal uptake from air or clothing is a meaningful exposure pathway for diethyl phthalate, diambutyl phthalate, for nicotine, and for BP3. Clean clothing can act as a barrier to dermal exposure, and clothing that has absorbed chemicals, it can accelerate the dermal uptake of the chemicals that the clothing has absorbed. Our skin is a reservoir. This is different from inhalation. When you walk out of a room where there's a high concentration of diethylphthalate, the inhalation exposure ends. But your dermal exposure continues. Your skin is this reservoir, and that's true for the phthalates and for nicotine and for BP3. By the way, what I just described for BP3, the paper describing the BP3 experiment has just come out in ESNT, so it's online now in Environmental Science and Technology. And the first author is Morrison, Glenn Morrison. This last point. Think about the clothes that are in your closet or in your drawer at home. Think about the chemicals that might be in the air of the room where your clothing is stored. Now, hopefully your bedroom is relatively clean, okay? But maybe there's some phthalates that are there at elevated concentrations, or maybe you've got mothballs there to keep the moths from going after your clothes, whatever. It's morning, you put on your clothes for the day, you're basically wearing the chemicals, the semi-volatile organic chemicals that have sorbed from your bedroom air to your clothes. You're wearing them for the rest of the day. And fortunately, the skin is a good barrier for most of those chemicals that the clothes have absorbed. But for certain chemicals with the right properties, they're coming into you through your clothes as the day proceeds. Well, with that, thanks for your attention, and I'll be happy to try and answer questions.
Thank you so much for so interesting, exciting presentation. Really great. I guess that we have some questions. By the way, I also say that we have done similar exposures, and I think that in your summary or in your presentation, we already found out issues why, and we found explanation why we see slightly different results. So all this makes sense. Yeah, we will continue with discussions after
I'm excited to hear about these results that Anita's speaking of. I haven't seen these yet, so this will be fun to discuss.
So this afternoon we will continue with this. But going back to this presentation and possible questions, is there anyone who would like to ask a question?
So for DEP, when the clothes were exposed, they were hanging there for about a week.
Correct, 9 days, so yeah, about a week.
So what if, in the example you take where it's your home, but I live there, okay? I don't just store my clothes, I live there. Is it possible to estimate the relative importance of this via the clothes compared to the direct to the skin and through inhalation?
We would have to know the air concentration of the target chemical. You remind me of something that I failed to say when I spoke about it. The larger the capacity of clothing for a chemical, the longer it takes to equilibrate with that chemical. So in the case of diene-butyl phthalate, 9 days was not quite enough to equilibrate with the chemical. For DEP, 9 days was enough to equilibrate. If we had exposed the clothing even longer, it would have had more diene-butyl phthalate. So we were maybe 75 to 85% of the way there. So back to your question, if we knew the gas concentration and if we knew how long it was exposed, we could make some estimate. And Glenn has developed a model to predict dermal uptake from clothing. And it's a dynamic model, it's a transient model, and pays attention to things like the air gap between the inside surface of the cloth and the skin. And so rough estimates can be made, but crude.
It is a significant route, or it is small?
It can be a significant route. So imagine that you're talking about a closet that for some reason has PVC in it. Maybe you have a PVC storage rack for your socks, okay? And that's emitting diene-butyl phthalate, okay? Well, the concentration of diene-butyl phthalate in that closet can certainly be elevated. Not that difficult in that situation to be up around maybe 500 nanograms per cubic meter, and the clothing will equilibrate with that, and then you're wearing the clothing, and it holds a lot of that diambutyl phthalate. So yes, it can significantly contribute to your body burden in an example like that.
Was another question, Morten?
Funny that you say it. It's exactly the situation at my home. My home was built '68 and all PVC flooring with these phthalates in it. I haven't actually measured it here. But my question was that if you extrapolate to other compounds that are more common nowadays than when we try to exchange the old phthalates to new compounds, do you think this clothing uptake will be more significant or less significant? Exactly that picture.
Yeah.
What's the trend, so to speak?
Okay, so Bill Nazaroff and I, the steady state model we originally developed, can be used to make an estimate of the overall permeability coefficient for a particular chemical. And if we look at some of the substitutes, let's take, for example, di-2-ethylhexylphthalate, which was a very common plasticizer in PVC. And one of the substitutes is DINCH. And DINCH is even higher molecular weight than DEHP. It turns out I didn't go into detail on this slide, but there's two parameters that really influence the permeability that you want to pay attention to. One is molecular weight, and one is the partition coefficient between the skin surface lipids and air. And the larger a molecule, the smaller the overall permeability coefficient. And that makes sense. You know, the larger the molecule, the more difficult it is for it to diffuse through the lipid bilayer. So DINCH, being significantly larger than DEHP, has smaller dermal permeability. And we can look at individual substitutes and make an estimate of how likely or unlikely they are to be taken up through the skin, either from the clothing or from the air itself. But I can't make a general statement. We have to talk about the individual substitutions that have been made.
But what property of the skin do you think are causing the individual differences that you see?
We're not sure. Now, another slide I didn't show is that for our phthalate results, our subjects at the time of the experiments, the youngest subject was 24, the oldest subject was 67, and we had a nice range. And the uptake increased with age. And it was scary how, I mean, it looks too good, okay? It's fortuitous, I think, that it looks as good as it is. But for those of us who are older, you know, it's not a message we like to see. In the case of the phthalates, it's like you're leakier as you get older. One of the reasons we think that is that the stratum corneum, although the number of layers remain the same, the layers become thinner with age. So the thinner layer means that pathway, that tortuous pathway, is actually shorter. So that might be part of the explanation. To what extent are the skin oils playing a role in the fact that the older subjects have less skin oil, skin surface lipids, than the younger subject? That might also be playing a role. But it's an area that if you look at the literature, there's just not that much in the literature on how dermal uptake varies with age. And some of it is confusing. You know, different research groups with different results. I do think it depends on whether the chemical is lipophilic or hydrophilic.
So can you measure this skin? I mean, have you used tape, strictly more, or?
Yes. A graduate student I worked with, she now She got her PhD. She's a postdoc at NIST in Washington, D.C. now. Her name's Moonyon Gong. And one of the things Moonyon did as part of her PhD work was skin wipes on human subjects in Beijing, on both students at the university, so these are people in their early 20s, and then she also did some work with school children. And she published several papers on that work, but the concentrations in the skin surface lipids, the concentrations that you measure with the skin wipes, are consistent with the gas phase concentrations. And there's a large US EPA study called CTEP, C-T-E-P-P, I forget what it stands for, perhaps you know of it, Martin, where they measured 100 children in North Carolina and 100 in Ohio, and they went to their homes and their daycare centers, and they measured concentrations in the air they had this about 20 semi-volatile organic compounds they were interested in. They measured air concentrations, dust concentrations, surface wipes, and hand wipes. And this is what got Bill and I first interested in dermal uptake, because we are using this CTEP database to look at partitioning between the gas phase and different compartments. And we decided to try to see how well the gas phase concentrations predicted the levels in hand wipes. And we were blown away at how well the gas phase concentrations predicted the hand wipe levels in this US EPA data for about 200 children. So yes, Bo, you can do surface wipes, and the surface wipes correlate reasonably well with the gas phase concentration.
Okay, I think that, is there anyone else who would like to ask a question now? If not, I guess that time is up for this seminar. Thank you very much to all of you for coming here. I just only mention once more that Charlie was kind to accept our invitation to our Center for Healthy Indoor Environments, and this seminar is also within the series of the seminars arranged within CAST, Consortium for Aerosol Technology and Science. Charlie, once again, thank you so much for being here and for giving this presentations. We really appreciate it. Thank you very much.